In a study that was published more than 20 years ago, lifespan was extended from 65 to more than 100% in fruit flies, otherwise known as Drosophila. So before getting into how they did that, let's take a look at the lifespan data. So on the top, we're looking at the percent survival for male flies, and on the bottom for female flies. And when looking at average survival, the point where half of the colony is alive and half is dead, we can see that average survival for the male flies was about 38 days, whereas for female flies, it's in the ballpark somewhere around 35 days. But then notice the significant extension in average lifespan, so the shift in the survival curves to the right for both the male and the female flies. So the lifespan, average lifespan in the male flies was increased by about 68%, and similarly by about 65% in the female flies. But also interestingly, note the increase in maximal lifespan for both the male and female flies. For the male flies, there was an approximate doubling of maximal lifespan from somewhere around 60 days to more than about 130 days. And although the magnitude of the lifespan extending effect wasn't as great in the female flies as in the male flies, nonetheless, the female flies also had about a 65% increase in maximal lifespan. So how was lifespan extended? Did they use calorie restriction, rapamycin, nicotinamide riboside, NR, or something else? So what they used is an experimental evolutionary approach. So what does that entail? So here we're looking at the force of natural selection on survival on the y-axis plotted against biological age on the x-axis. And what we can see is that during childhood, the force of natural selection on survival is very strong, such that survival is about 100%, so basically no mortality rate. But once we hit the first age of reproduction, we can see that the force of natural selection on survival starts to fall, all the way up until the last age of reproduction, and at some point in the near future after that, death. So with this in mind, if you delay reproduction, as they did in this study for both the male and the female mice, until the last possible point in these curves, you can extend lifespan, and that's exactly what they saw. So and by doing this for many generations, and actually for thousands of generations in the fruit flies, that led to this significant lifespan extension. Now, the lab that was responsible for these studies is of Dr. Michael Rose, who is a distinguished professor of ecology and evolutionary biology at the University of California, Irvine, and he's also the director of NEAR, the Network for Experimental Research on Evolution. I recently had the honor of having a conversation with him and asking him about these findings and how we can potentially translate them into human longevity and a whole lot more. So this is the first part of that conversation. So let's get into the conversation. Enjoy. I want to jump right in, and I think a lot more people in the aging space know about you. And it wasn't like that 10 years ago, which is crazy. I knew about you, but most people didn't still. So I think it's important that we start from your lab being one of the few, if the only, that's extended lifespan without using drugs or any pharmaceuticals you can think of, or calorie restriction. So I think a good place to start would be the experimental evolution approach, explaining that, and then going into the magnitude of the lifespan extension that you saw as a result.
Okay, well, thank you for this opportunity, Mike. And it's great to be interacting with you like this.
Cool.
I've been admired your stuff for some time.
The honor is all mine.
So in 1977, at the University of Sussex Library, I was reading an article by a very early gerontology person called Wattier, a Belgian, who actually had worked in the lab of Theodosius Stajansky, but Wattier was Neo-Lamarckian, and he was looking for Neo-Lamarckian effects on lifespan. And he did an experiment where he bred flies exclusively from older adults. He did this in two different Drosophila species, Subobscura and Pseudoobscura. And in both cases, he got an increase in lifespan, which he interpreted in terms of a Lansing effect, or an inverse Lansing effect, because when Lansing did it, the fly, his staffing had died out for completely different reasons. I read the article and I thought, oh, he modified the first stage of reproduction, which according to Hamilton's forces of natural selection, means that given enough time, these populations should evolve to late aging. And which was not Watteau's interpretation of his own experiment whatsoever. So I thought, well, why don't I do a cleaner version of this experiment using nicely outbred fruit flies, which I did during my doctorate at Sussex in the 1970s. And it worked just as well for me in my one population pilot experiment as it had for Watteau. And I wrote up that experiment and a few others that I'd been doing during my doctorate. I sent them off to an obscure journal called Nature, which published the article in 1980. It's called A Test of Evolutionary Theories of Senescence. And I was so enamored with this very simple experimental evolution project where you just change the earliest stage at which you allow an organism to reproduce, and then you take advantage of evolutionary genetic theory, the most hardcore theory in all of biology, and it does the work for you. Only the second time I did the experiment, starting in 1980, I did it with 5 populations with delayed reproduction and 5 control populations. And off we went, starting in February of 1980. And those populations still exist. I sold them to an anti-aging company called Methuselah Flies, which still owns them. And I still work with them intermittently as a consultant to various companies that are interested in working with those. Since then, in my lab, University of California in Irvine, we have taken lifespan up using experimental evolution. We've taken it down using experimental evolution. We've taken it back up again. We've also modified lifespan using diet, using drugs, as have other people. So I have been manipulating aging since 1977, as well as studying its underlying genetics, genomics, and transcriptomics in partnership with many other people ever since the 1970s. And all of the work suggests that aging is not an uncontrollable process of molecular damage. It is instead the tuning of adaptation relative to age, which is easily done by natural selection, which indeed, through its dereliction of doing that job, engenders aging. And the genomic means by which natural selection tunes aging involves hundreds of sites in the genome. Not 1, not 2, not 7, hundreds, as I said in dozens of interviews over the last decade. And that in turn tunes hundreds of transcript levels, both qualitatively and quantitatively. And it in turn tunes hundreds of metabolites of all different kinds. And then it retunes all the organ systems in the flies. The hard thing is to find something that is not connected to aging. Almost everything is connected to aging, even in a very simple organism like a fruit fly. And I would say very confidently, by way of extrapolation, I think in humans also.
So you started from the same founder group of flies, and then you separated them into the long live versus the short live, or is that's basically the
well the material protocol is to tune the life cycle. If you tune the life cycle so that there's a long period of time between when an egg becomes or is given, the adult that is produced by the egg is given the opportunity to reproduce. The longer that life cycle is, the greater the lifespan that population will evolve. And it does so at considerable speed. And then if you then reverse the procedure and take long life cycle flies and give them shorter life cycles, they will rapidly evolve shorter lifespans. And so going up, going down, going up, going down, that's something I've now been doing for 44 years.
Yeah, so that approach is clearly showing that you can use evolution to extend lifespan, and not extend it by a little bit, by 10 or 15 or 20%, you know, by
2 times, 3 times,
yeah,
5 times.
yeah. So the
Yeah.
question is, how many generations did it take before you saw, say, a doubling of lifespan in Drosophila?
The doubling of lifespan took about 80 generations.
80 generations. So 25 years, if we're going to extrapolate that into human years, right? 25 years per generation. So we're looking at what, 2,000 years? 80 times 25?
Right. So together with my very good colleague Larry Muller, we published a paper in around 1990, somewhere between 89 and 91, about 30 years ago, on how long it would take if you wanted to use this approach with human lifespan. And it's not worth doing. So actually, since 84, at the instigation at first of journalists and then by more and more people that I've met over the last 37 years, I've been working on coming up with faster and faster ways of doing this that don't involve experimental evolution.
So, okay, can you tell us more about that, or is that
Sure. So we published an article in what was it? The early two. Let me try to get the year. Circa 2010, in a book called The Future of Aging. It was edited by Greg Fay and Steve Coles and a couple of other people, where we outlined one idea that a company called Senescence was founded on, and that company still exists. That was basically a layered supplementation approach, very Mike Lusgarten, I might say, except instead of experimenting on Mike Lusgarten himself, the idea was to experiment with fruit flies and see what we could get to work there, and look at the omics of how it was done in fruit flies, and then use an omic bridge to humans, because so much of our genomes, our transcriptomes and metabolomes overlap. So it would have been an omic guided bridging to human intervention. So that was a technology I was very enamored with 15 years ago when that company was founded. Then I founded another company with a man called Larry Cabral about 6 years ago. It's called Lyceum. And that was based on another strategy. And I don't know if the company has mostly ceased doing business, but the website might still be up. And so I've gone through a whole succession of technological ideas for how to intervene in the human aging process that do not involve experimental evolution. And I'm still interested in that project.
So I guess the idea would be to come up with a cocktail of as many different, or supplements, drugs, etc., as possible to kind of replicate the multi-omic signature that you see in the extended lifespan, dramatically extended lifespan in the fruit flies. But I'm guessing that that's going to fall short, because I mean, you're, as you mentioned, you're dealing with hundreds of genes and then hundreds of transcriptomic sites, and then maybe more than that in terms of metabolites. So how close were you able to get using the multi-supplement drug-based approach in terms of extending lifespan in flies?
So Genescient made a good start on that project, and that research actually led to a supplement which is available right now. It's marketed by a company called Genair, A-I-R-E, and I can't remember the name of the product, but you can look up the company name on Amazon. I was not directly involved in developing that product or testing it, but it used some of my ideas. And I guess, I think they called it Rebuilder or something like that. Right now it's being marketed as a cognitive health product. Since I left Senescence in 2010, for the last 11 years, I've been very interested in using AI, more precisely machine learning, to master the intricacies of going from fruit fly genomes to human genomes, of going from omic effects to clinical efficacy in humans. We are now engaged in a series of publications which started in 2017 with a massive genomics paper. And then in 2018, we published our AI methodology, which is called FLAM, F-L-A-M. Well, we didn't develop the machine learning tool. In that article, first author is Muller, M-E-L-L-E-R, L-D Muller, I'm the last author. That presents some of the machine learning we use. Then in 2019, we published a transcriptomics paper. We are working on metabolomics stuff. Haven't submitted a manuscript yet. In parallel with my aging career, I've just generally worked on quantitative genetics of adaptation. And aging is just, in a sense, an aspect of adaptation. Right from my earliest work on this stuff in the late 70s, it was quite apparent that the genetic foundations of adaptation and aging are complex. So one of the things I have worked on very hard over the last 41 years is strategies for unpacking the complexity and making our way through complexity, both from the standpoint of scientific inference and from the standpoint of technological intervention. As some of your listeners or viewers may already know, I did a website called 55 Theses, T-H-E-S-E-S, modeled after Martin Luther, 95 Theses, but shorter, and earlier, where I try to outline the insights that I had as of 10 years ago. But over the last 10 years, we've made a lot of additional progress, which we're trying to publish. I mean, we are publishing it in this sort of sequence of papers that started in 2017. You can find them on my Google Scholar page, Michael R. Rose, and most of our publications since 2017 are in this vein. And there'll be more to come over the next 3 years. We have one under review, under endless revision with the journal. I will not name to protect the guilty. So I think by 2023, people interested in genomics, people interested in adaptation, people interested in aging should all have a pretty clear understanding of how complicated the core omics foundations of all this stuff are, and also how machine learning can sort through all these things, and thus potentially, furthermore, how we can bounce back around, going from fruit flies to humans, humans back to fruit flies, and make all the connections thanks to homology. Because it turns out that the metazoan toolkit for adaptation and for aging has huge overlaps. When you do experiments with Drosophila, or for that matter humans, you're not just studying Drosophila or humans. You're studying basic features of aging, adaptation, and genomics that are in common between metazoa the majority of the time, the clear majority of the time. And we're going to be making that quite clear. First with Drosophila, then we'll be doing some projects with humanomic data and say machine learning tools and using